Hey everyone, welcome back to another lab video. So this is lab 7 on simple linear regression. Depending on when you're watching this video, I want to either wish you good luck on the upcoming midterm or congratulations on finishing the midterm. So this lab is due the Thursday after the midterm, March 11th. So maybe you watched it before, maybe you watched it after, but in any case, I hope you did well. And yeah, congratulations on reaching the midway point of the class. So anyway, lab 7, simple linear regression. Let's go ahead and import AutoGrader. So this lab will be very similar to lab 6, the previous lab, in which case we're going to do the same thing a bunch of different times, but using a bunch of different methods. So in the previous lab, we talked about the constant model and minimizing loss for the constant model, and we went through and we looked at the graph and did it by inspection. We went through and did an optimization algorithm. Then we found a closed form solution. In this lab, we'll do something similar for figuring out the parameters of our linear regression models. So one way we can do this is we'll be using Seaborn. We'll be using the analytic solution, so that's synonymous with closed form. We're using the optimization algorithm, and then also we'll introduce you to sklearn, which is like the big tool used in data science and machine learning. So as this little note here says, like in real world data science work, you're probably not going to be like hard code, like writing your own linear regression optimization algorithm. You'll probably just use what sklearn has already done for you. But it's really helpful to do this as an exercise so that you actually know what sklearn is doing, like what it's doing under the hood, so to speak. As I said, lab due March 11th. List your collaborators. This is kind of like the squad of Data 100 imports. This Pandas, NumPy, Seaborn, and Matplotlib. This cell here just says, hey, don't yell at me and if there's a deprecation warning. If something's going to be deprecated, I don't care about it. Don't tell me. I suppose if we got rid of this, there would be a bunch of deprecation warnings, but who knows. So we're going to go ahead and load the tips data set again. So this is the same data set from last time. Last time we just looked at the tip column. So we had literally just the tips. We didn't care about any other information. Now we're going to be incorporating some other information, notably total bill. But this data set also has information like the day of the week, whether it was dinner or lunch, the size of the party. But we're just going to be talking about total bill and tip. So again, we did the constant model. There you go, you can see it. So we have just one theta value, one parameter, and depending on our parameter, the value of our parameter, we'll get a bunch of different losses, and we want to find the parameter that minimizes the loss. And we did that with both squared loss and absolute loss. In this case, we're going to have two parameters. We're going to have one corresponding to the intercept of our linear regression model, and another corresponding to the slope of the x value. So in lab 6, we did not incorporate any x values whatsoever. We were just saying, hey, given the tips, what's the one singular value that best sums up all the different tips? Here we're actually saying, oh, I'm going to incorporate tips, or I'm going to incorporate total bill. I'm going to incorporate some sort of x value. So maybe that will help out my prediction. I'll get better predictions. I don't just want to predict the same tip for all tips. That doesn't make much sense. Maybe I know that total bill has some influence on tips. So I want to incorporate that and make a better prediction of tip. So in lecture, you may have seen these be called theta naught and theta 1. I think, or in this lab, we'll just call them A and B. And yeah. So the first thing we can do is we can call .lmplot. So what this is going to do is this is going to show us a scatter plot of total bill. So total bill is the x because it's just our independent variable, what our predictions are based on. And then we have tip, and tip is the y value, the response variable. And you can see the scatter plot here. Cool, cool, cool. We can see, okay. We also see this line here. And this line is the regression line. Seaborn just calculated it for us itself and just put it there. That's what calling lmplot does. Don't worry about these little bands surrounding the line. If you're interested in what they are, take an advanced stats class. I think 135 and 151 both discuss this, but don't worry about it for the purposes of this class. But yeah, anyway, We literally just called seaborn sns.lmplot, said, here's my x, here's my y, and then it says, oh, here's the regression line. We didn't have to do anything at all. There it is. So now what we can do is we can actually figure out exactly what these parameters are. So in lecture 12, we derived the following expression for the line of best fit, aka the regression line. And we have y bar, x bar, so that's the mean of y and x, this correlation coefficient r, and then the standard deviation of y and the standard deviation of x. So we calculate all these things, and then we plug in some xi, so xi being, in this case, the total bill for a new table, a new party, the total bill. And then we have y hat I. So given this total bill, y hat I is, oh, what's my prediction for the tip based on the total bill? So here's the formula. Maybe it looks kind of crazy the first time you're seeing it. Hopefully this is not the first time you've seen it. Okay, yeah. So we can go ahead and calculate all these different terms here that we're going to use to build our predictions and build this formula. So x bar and y bar are fairly straightforward. We can literally just call np.mean on tips of our x variable, which in this case is total bill, np.mean of tips tip. And then standard deviation, we can call np.std of tips total bill again, because it's x, and np.std tips tip. Just a note here, make sure you use np.std. Something else you theoretically could have done was you could have said tips total bill .std and literally called like .std on the series itself. The reason why we don't want to do this is that these two functions, they use slightly different formulations. If you're a statistics major, you know about like the n-1 on the bottom versus the n on the bottom, and that's the difference between these two formulas. We want this one. We don't want this one, so don't do this. Even though it is theoretically possible, for the purposes of this lab, we don't use this formula. Use the one I left here. And then to calculate the correlation coefficient, we're going to use np.corrcoef, as you may have seen in homework or in lab, or in this lab, in lecture I meant. So np.corrcoef, it can take in the x. So x again is total bill, and y is tip. You can see, well, what does it return? Well, it returns this two-dimensional matrix. It's a 2x2 matrix. And we see the diagonal values. The diagonal values are both 1. Well, why are they 1? Well, that's because they represent the correlation between tips total bill and tips total bill. And those are the same thing. It's the same column, so they're going to have perfect correlation between the two. And likewise for down here, tips tip and tips tip have perfect correlation. But so what we actually care about, the correlation between tips total bill and tips tip, is what's on the diagonal here. And they're both the same, so we just have to select one or the other. And I'm just going to select the one in the top right, and that's how you might do that. So we can go ahead and copy that down here. Okay, there we go. Typo. And we go ahead and we pass the test cases. Awesome. So now we have all that stuff, all of these terms in here. Let's actually calculate what a hat and b hat are. So b hat's a little bit easier to find. Again, b hat is our estimate of the slope of the regression line. And you can see, well, what's the slope? Well, it's the stuff in front of the xi. That's r times sd of y, which is std y, divided by std x. What's a hat? Well, a hat is the estimate of the intercept. And the intercept, there's y bar, but it's not just y bar, because we also have this x bar term here, which has this other stuff in front of it. So we also have to consider the term with x bar in it. And I could have just written, I could have just copied this down here. That's why they gave a hint saying you may want to define a hat in terms of b hat, because notice how kind of this term is b hat, and it also is out in front of this x bar. But I'll just go ahead and say b hat. And we pass the test cases. Awesome. So now that we have A hat and B hat, we're going to figure out where we're going to make a prediction for a bill of $20. So let's say the total bill is $20. What do I predict the tip to be? Well, this is fairly straightforward. We can literally just do A hat plus 20 times B hat. Y equals A plus BX. And we say it's about $3.02. Okay, cool. Is that good or bad? I don't really know. But that's just what we predict given our calculations. Now what we're going to do is we're going to, instead of just predict for a single point, a single table, a single party, we're going to predict for all the tables in our data set. So all the different parties throughout the night. A table might be kind of confusing actually, because in this case I'm referring to table as in like the literal like table in the dining room. But yeah, each individual row we're going to predict the tip based on the total bill. And the way we can do that, I guess supposedly you could write a for loop, but hopefully we burned into your brain that you should use vectorized code instead. And what I'll do is I'll just replace the 20 with tips total bill, because tips total bill is basically our x, and we can leverage vectorized code to calculate the predictions for all of our rows in x. Okay, pass, awesome. If you define it correctly, you'll see a scatter plot, and here's a scatter plot. So we have total bill on the x-axis and tip on the y-axis, just like above. And you can see in red, we have the regression line. So cool. I mean, here's the regression line. It's the exact same regression line that we see above. It looks a little bit different here because like the scale is a little bit different, like the ratio, the color is different, obviously, the points are bigger, but it's still the same data in the same exact line. And there you go. That's really all there is to it. So now here's what R is. So R, we kind of saw before, it's about 0.675. Well, what does this actually mean in the context of the scatter plot? Well, the first thing you should ask yourself is this positive or negative? And the answer is, well, it's positive. And a positive correlation means that there's an upward positive relationship between total bill and tip. And hopefully you can see that, like, as total bill increases, so generally does tip on average. It's not always the case. For example, here's a tip, like here's a total bill of about 30 and a tip of about 6. Here's a total bill of about 45 and a tip of about 3. So it's not always going to be the case that as you increase total bill, tip increases, but on average, it'll increase. So that's the first thing we could say is it's positive, so upward relationship, something to that effect. Another thing I would ask yourself is, well, what about kind of the magnitude of R? If R is very close to 0, that shows that there's not much of a relationship at all between total bill and tip. Meanwhile, if R is super, super big, like it's very close to say 1, like 0.95 or whatever, then we'd say that there's a definite, clear, very strong positive relationship between the two. Well, it's not really super small, it's not really super big. And I think that's evidenced in the scatter plot. We can see that it's definitely upwards. It's definitely increasing. It's definitely pointing up. But it's not, they're not super compact close to this line. It's not a super strong relationship. So that's what I would say. I would make some comment about the magnitude. I would say not super small, not super big, clear positive relationship, but not super strong. That's kind of a bit hand wavy, but just some comment interpreting the magnitude of this R value is what is required here. So that's that. That's question 1. So now we can go on to question 2. So in question 1, we literally found, like we plugged into a formula and we found the values for A and B that minimized our loss. We derived it in lecture, and here we go. We implemented it in lab today. Instead of implementing a formula, we can instead call an optimization algorithm. We can say, hey, here's a function that evaluates the loss. Find me the A and B that minimize this. And Python will go ahead and do that. So we can define the risk of our model. So that's, again, yi minus y hat squared for each data point, sum up, divide by n. So the average squared loss for each data point. And we can call that the risk. And we define that in the function as L2 tip risk of A and B. So it takes in 2 parameters, A and B, and it spits out the risk. So you can see that if we plug in values that are close to the ones that we found before, we'll get a pretty reasonable, like pretty small risk. So these are close to what we got before. If we plug in something completely different, maybe we plug in like 120 or something, obviously now our loss is huge because our parameters are really far away from what they should be. So, um, so yeah, we want them to be close to what they should be. So what we can do is we can use this minimize function that we saw in the previous lab. And so yeah, so let's go ahead and do that. There's one problem with this, is that this function takes in two parameters. It takes in A and B. The minimize function, the minimize like optimization algorithm, it doesn't know how to handle that. It says two parameters. What? Huh? I don't know what to do here. The way we can get around this is because of course functions are going to have many different parameters. Like it's unreasonable to expect that you're only going to ever have to minimize like one variable. You want to minimize the function and it has multiple variables. The way to get around that is to define a list which contains all the different variables, all your different parameters, and then just pass that in as a single value. So here's a silly example here. We just have a quadratic, like a two-dimensional quadratic, so to speak, u and v, and here it is. Instead of saying f of u and v, what we can do is we can say f of a list, in this case we're calling the list data, and then subset into the list and do the calculations, and minimize will actually work exactly as we expect it to. Notice how x here, x is like the minimizing x. X is now an array, also a list, 1.5, 1.5. And that's, we said it above that the minimum value of this function occurred at 1.5, 1.5, and SciPy was able to find that. Surprise, surprise. So now we're going to go ahead and we're going to rewrite the above risk function such that it only takes in one variable. It only takes in one list that is theta. So this A and B, it's kind of annoying, so we're just going to worry about theta. And as in the usual style of labs, I'm going to just copy the code from above. And then instead of saying A and B, we can just say theta 0 and theta 1. And that way we pass in a two-dimensional list into this function, and then the calculations will still work out exactly the same. The first element of this list is going to be A, and the second element of this list is going to be B. Pass the test case, great. So now what we can do is we'll call minimize, again, copy the provided code. And instead of F, we want to minimize L2 tip risk list. And then we have to set X naught, so X0 or X naught. That's our initial guess, like the starting point of this algorithm. In this case, it doesn't really matter what it is. I'm just going to set it to be 0, 0. You can set it to be whatever you want it to be. And let's go ahead and look at the output. And we can see that, okay, the minimum loss is about 1.036. And here the X value that minimizes this, this loss. So it's not really X here, because remember when we're talking about our model, X is the data. Here, X is like what's being like passed into the minimizing function, which is really A and B. So this is A and this is B, even though just kind of the Python module SciPy calls it X, but really it's A and B. And we can see we get 0.92 and 0.105. And just to compare that to what we got before, so A hat SciPy is what we got just now, A hat manual is what we got in question 1. And we could see that they are very, very similar. They're down to about 5 or 6 decimal places. Well, why are they different after 5 or 6 decimal places? Well, that's because SciPy, the optimization algorithm, it got close enough and it said, okay, I'm done. It could have kept going and going and going and going and gotten down to like the 30th decimal place, but we didn't want to do that. That would take too long. We consider the 6th decimal place to be good enough. So it just stopped there. So this is what we got, again, just by plugging in a formula. This is what we got by running a numerical method and optimization algorithm. And you can see that they're basically effectively the same. Okay. So we've done that. So now we'll go ahead and use sklearn. So sklearn It's not super important now, but you're going to be using it on a lot of assignments coming up, logistic regression, decision trees, so on. And scikit-learn is good to know because if you actually go and do like a research project or go work for some company, chances are you'll be using sklearn to do these models. So how do we do that? Well, we can import the linear regression model from this module. And the way we kind of work with this and do these calculations is through this model object. So what is a model object? Well, a model object contains all the details about your model. It contains the data that it was fitted with. Once you fit it, it determines like it contains like the optimal parameters. It contains like it has methods that allows you to predict data. So it basically stores all the information that you need about the model. The way we initialize a model is calling just linear regression, open parentheses, close parentheses. This basically initializes a new model and we save it in the model object. And now we need to fit it. So we can just run .fit. Here's our x and here's our y. X and y. Why are we passing in a data frame to x if we only have one x variable? Well, that's because in general, scikit-learn can take in multiple different x's, and we'll see that in a few minutes. So it doesn't want to kind of like pigeonhole you into only doing simple linear regression or multiple linear regression. It just says, hey, give me a data frame. I don't care if that data frame only has one column. If it only has one column, that's fine. But just give me a data frame as opposed to just a single series. So that's why we use the double brackets here as opposed to single brackets. So now that we fit it, we can look at what the coefficients are, and we see the intercept again, 0.92, seems familiar from above. So that's like our A hat value. And then our B hat value is in this .coef, attribute, and it's 0.105. Okay, cool. Scikit-learn can do the same thing as what we just did manually ourselves a few minutes ago. If we want to predict, we can use the model predict function. We don't literally have to say 20 times model.coef. Like we don't have to do that. We can just call model.predict. And we can go ahead and it'll predict 3.02 for $20. So just if our bill is $20, scikit-learn predicts $3.02, just like we saw way back in question 1. Why is this a 2D array if we're only inputting a single value? Well, that's because, again, in general, we might not have just one data point that we care about. And each individual data point might not just have one feature. It might have many features. So in general, like our x that we want to pass in, it can be like a 2D matrix, even though here it's literally just like a one by one point. So that's why we have to wrap it and make it a 2D array. Okay, so now what we're going to do is we're going to create the predictions. We're going to find the predictions for each point in our data set. So we're going to kind of, for each point, we know the total bill. Technically, we already know the tip, but we'll just predict the tip given the total bill. So we can do model.predict on tips total bill. Again, I have to use the double bracket notation because it takes in a data frame. And you see, surprise, surprise, the same scatter plot that we saw in question 1, the same data, the same regression line, not super exciting. One note that I'll mention now, but probably won't come up for a little while, but when it does come up, it's very important. Whenever you're calling model.predict, this takes in something, basically like your new x, and it has to be in the same format as the x which you passed into fit. So here we passed in tips total bill. Here we're actually passing in the exact same data. But in other cases, and plenty of other cases, as we'll learn very soon after the midterm, we don't want to be predicting on the data that we fit on. We want to be predicting on new data that we haven't trained our model on. But in that case, it's not going to be the exact same data. But in that case, we need to make sure the data is exactly in the same format as what we call .fit on. So this isn't super interesting now, but you can imagine a case maybe we do some modifications to total bill. Maybe we like scaled it or subtracted it, or maybe we added new columns or whatnot. I'm kind of getting ahead of myself a little bit here, but I want to stress this now. So, because that's like the #1 solution in office hours once we get a few weeks down the line. Make sure you do that same processing on the data that you pass into .predict. This data, this expression here has to be in the exact same format as this. In this case, they're exactly the same data too, but it probably won't be the same data, but it has to be in the exact same format. Okay, I think that's enough about that. So now, okay, we're kind of going to be leaving the TIPS data set. We're going to go on to this other data set, multiple linear regression. And we can just extend the same lines of reasoning from before. So instead of a plus bx, now we have theta naught plus theta 1 x1 plus theta 2 x2, so on and so on and so on and so on until we, for all of our features that we have. So in this case, we say we have p features. So yeah. Note that the term features, independent variables, and explanatory variables, like they all mean the same thing. Someone posted a great meme in the summer 2020 edition of this class, where it was like the Spider-Man meme, like we like keep pointing at each other. And there were like 6 different Spider-Men there, and they all labeled like explanatory variables, independent variables, design matrix. So there's tons of terms to represent the same like X values, is what I'll call them. So here we go. We can load in this other kind of default data set called MPG. You can see it's data about cars. So we have miles per gallon, we have cylinders, model year, the name of the car, horsepower. Cool. So we can look at horsepower and miles per gallon, looking at this vehicle data. And we can see horsepower on the X, miles per gallon on the right. And you can see there's a clear downwards trend. So maybe let's fit a regression line. So we can do that. We can call .lmplot from Seaborn. And we can see that the line doesn't do a very good job. For example, if horsepower is really, really big, the line comes nowhere near any of the miles per gallons. Similar for if horsepower is really, 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 really small. We don't come anywhere close to the actual MPG. And that's because, I mean, maybe you kind of looked at this right away. That's because the relationship looks curved. So a linear model is probably not the best fit. And you can kind of emphasize this. A way to emphasize this is with our residual plot. So a residual plot, instead of plotting like X and Y, it plots our fitted values versus the residuals. And as you can see, there's a clear curved trend. As our fitted value increases, the residual, it's like a kind of like a U-shaped parabolic trend. Ideally, what we would see was we would see a bunch of random noise and there would be no pattern whatsoever. But here there's a pattern, and patterns in residual plots are bad. Downvote. It's an indicator that we still have there's still something that we haven't accounted for in our prediction. So what we can do instead is we can say, this looks kind of curved. This looks kind of curved. I wonder if we should include like a quadratic term. And that's exactly what we can do. We can add a quadratic feature to our design matrix, or just to our data. And then you can see that this is just the square of horsepower. So remember, we were trying to predict miles per gallon based on horsepower. A linear model didn't make sense, but maybe a linear, maybe like including a quadratic term will help. So we can go ahead and let's do this. So we have to make the linear regression object, which is already defined for us. And instead of fitting on vehicle data and horsepower, we can fit it on horsepower and then this new HP squared term. And instead of it being model simple, model multiple. So here we're just using two X variables. And this is why, again, it's a data frame as opposed to a series. So we can go ahead and run this, pass, awesome. We can see our coefficients. Cool, great. I don't really know, like, are these good? Are these bad? Those are not immediately obvious. So what we can do, well, what it's telling us to do is just to literally write out this expression in math using LaTeX, the famous LaTeX. So I'll just say I'll call M equals MPG, H equals horsepower, and then I'll say our prediction for M, so M hat, equals 56.9 minus 0.466 times h plus 0.0012 times h squared. And there you go. There's the expression in LaTeX. Now, if we look at this and plot this, we can say, oh, it looks a lot better. We can see that our model is now capturing some of that curvature that we saw before. It's not super perfect. It's definitely not perfect. For example, again, if horsepower is really big, most of the points are underneath the curve. So that's still kind of not great. Like, we're not super happy with it. But this does a hell of a lot better job than the one that we did before, because we're actually able to capture this curvature in the data. Okay, why is this model still linear? That's kind of an interesting question. Like, it doesn't look linear. It looks like a curve. How are you going to tell me it's linear? It's a curve. Come on. Well, the reason why it's linear is because I think a good way to think about this is that the linear regression, like sklearn, the linear regression module, like the equations that we use, they don't care that this column happens to represent horsepower squared. For all sklearn knows, for all the normal equations know, for all the different algorithms know, this is just another column. It could be something completely different than horsepower squared, and the equations would work, the algorithms would work just the same. But we, as the data scientists, have made a determination to have this new column represent exactly horsepower squared. So it's still a linear model. It just so happens that one of the terms, like one of the features in our linear model, represents horsepower squared. So that's kind of like a good reasoning. So I would say, well, still linear as HP squared is its own feature. sklearn doesn't care that it happens to be a, like, we could have replaced, like, instead of h squared, it could have been like some other variable, like, I don't know, like j or something like that. And maybe we have some j variable, and again, everything would still work exactly the same. We'd still have a theta for the intercept, a theta for the first term, a theta for the second feature. It just, again, the second feature just happens to be horsepower squared. It doesn't just happen to be horsepower squared, like that's this conscious decision we made, but according to, like, from the point of view of the math, it doesn't matter. Okay. So now what we can do is we can look at this capital R squared. So remember, capital R squared represents, or equals, the variance of the fitted values compared to the variance of our actual y values. Now, what does it mean? Well, it's the fraction of the variance in our actual y data that is captured by the model. So ideally, this would be close to 1. It would be very close to 1. If it's close to 1, great. We did an awesome job. We captured most of the variance. We have a great model. But in practice, it's not always going to be close to 1. And we can see the difference. So if we only use horsepower, it's about 0.61. Okay, fine. Like, I don't really know how to interpret that. Seems reasonable. If we use both horsepower and horsepower squared, it goes up to 0.687, so on and so forth. And that means that's an indicator that it's doing a little bit of a better job. We'll be able to capture more of the variance. So now what we can do is this is kind of a related question. So we have here the mean of our miles per gallon data. So the mean miles per gallon. So given this, how do we figure out the mean of our predicted values, both for the model with horsepower squared and for the model without horsepower squared, so just horsepower? This is kind of a trick question. And the answer is that it's literally just this mean. The mean of our predicted values is going to equal the mean of our actual data, assuming that we have an intercept term. I think in lecture and in the homework, you show the x bar and y bar, like that point is on the regression line. It's kind of the same line of like rationale here. Just the mean of our predictions equals the mean of our actual response variable. Okay, awesome. Finally, last question. So now we're going to introduce a few more features. So instead of horsepower and horsepower squared, we also have model year and acceleration. So they define it as model many. They include all these different columns, and they fit. So what we have here is looks kind of crazy, like a crazy line. And that's because it's incorporating the model year and the acceleration. The reason why it looks so crazy is because we're only looking at horsepower and MPG, even though model year and acceleration have an influence on these predictions. So you can imagine this is kind of like a cross section. Like imagine we're looking at like a 4D, you can't really visualize 4D, but imagine we're looking at like a 4D graph and we're just looking at a 2D slice of the 4D graph. This is what it would look like. And that's why it doesn't look linear at all. It doesn't look quadratic at all. That's why it's all jaggedy. That's why it looks the way it does. Okay, answer. That's why it's so jagged. So now what we can do is we can figure out the r squared value of this. And what is r squared? Well, capital R squared is the variance of our predicted values minus or divided by the variance of our actual values. So what's the variance of our predicted values? Well, that's calculated for us here when they did model many.predict. They called it predicted MPG many. And then we already know that this is the variance of our actual y values. We can calculate it, and great, we pass the test cases, and we can actually see what they are. So here's from the first two models, horsepower and horsepower squared. And now we're actually looking at using everything, or not everything, but using these two additional columns, model year and acceleration. And you can see that our r squared has increased even more. So great. Yeah, we've captured more of the variance. Awesome. Capital R squared is not the be-all end-all. As we'll learn very, very soon, if we can just keep adding features and features and features and keep increasing our R squared, and maybe our model isn't going to be getting any better. Maybe it'll actually be worse if we increase a bunch more features. So don't just look at r squared and say, oh, I've increased r squared. Awesome, yes. Like my r squared is 0.95, yours is 0.87. My model is better. No, that's not necessarily the case. But it is a decent indication of how well your model is doing. So that's the lab. I'll go ahead and save, kernel, restart, and run all. So that's the lab. Hopefully it was helpful. Maybe a little bit of a longer video this time, but that's okay. And yeah, good luck on the midterm if you haven't taken it yet. Congrats on finishing the midterm if you have. And I'll see you next week.